think so. Okay, so we are going to start the afternoon session. So maybe we can get started. So as Emmanuel said, I will talk mostly about the Bombieri-Vinogradov theorem, which I'll try to explain a complete proof of in my lectures. And I'll also talk a little bit more generally about sieves, at least a large sieve, which I'll need for the Bombieri-Vinogradov theorem. But before I get to that, maybe I thought today I would speak of a more basic and fundamental sieve method, Selberg sieve, which also plays a very important role in the proofs of Goldstone, Prince, and Yildirim, and also of Maynard and Tau. And James will build on that in his course later this week. So again, as we mentioned at the beginning of this workshop, it's a very diverse group here, and we the organizers or the lecturers don't really know what you know and what you don't know. So again, I encourage all of you to speak up if you're not sure about some step, and I'm always happy to go over it. Or even if we don't do it right here, we know what we can punt to Zeb and Benny, and then they can take care of that sometime later on. So again, stop me whenever you feel like. So Dimitris was talking mostly today about pi of x, the number of primes up to x, or the number of primes in a given arithmetic progression A mod q, where A and q are coprime. And what he was describing was really the analytic approach towards understanding this. But you can also think of primes are just numbers up to some point. So you can think that there might be some kind of combinatorial way of just thinking about primes, say. For example, by understanding the primes as all the numbers that are not even, all the numbers that are not even and not multiples of 3, or multiples of 3, multiples of 5, etc., etc., and then try to do some kind of inclusion-exclusion to try to get your hands on primes. And this is kind of the heart of, or the germs of sieve theory. So for example, concretely, you might say something like the number of primes up to x would be the number of integers up to x minus the multiples of 2 maybe I should put double dots here, minus the ones with 3 dividing n, etc. But then adding back with inclusion-exclusion those numbers with 6 dividing n, or 10 dividing n, and so on, and then subtracting the ones that are multiples of 30, etc., etc. Or in other words, you could see if I use the Möbius function, then this is like counting okay. So what should it be counting? Well, okay. There's some kind of problem here. I don't want to subtract everything that are multiples of every prime, right? Then I'm going to be left with nothing. Or maybe I'll be left with the number 1 if I do inclusion-exclusion with that. But I could now make use of the fact that primes are those numbers up to x that are not divisible by p divides n, let's say, implies that p is bigger than root x. Yeah? If a number is composite, then it probably has a prime factor which is less than root x. That's not really the number of primes up to x. That's the number of primes up to x minus the number of primes up to root x, and maybe adding 1 for 1. And then this is fine. some expression like this is fine. Okay? So assuming here that I stop after p getting up to root x, and then here I just take products of numbers that are primes less than root x, and then subtract the ones that are products of 3 primes less than root x, and so on. Is this good? Okay, so in other words, inclusion-exclusion tells me something like this, that this is the sum over all numbers d that are divisors of the primes below root x, okay? And then I sum things with these weights, which is 1 for 1, minus 1 for 2, or minus 1 for a prime, plus 1 for products of 2 primes, and so on. That's the Möbius function mu of d. And then I'm counting here the number of integers n up to x with d divides n. Okay? So this is the most basic version of a sieve, and it already tells you some features that are common to all sieves, that you have to, in order to get some information out, you have to put some information in, and the kind of information that you're going to put in will be your sequence numbers up to x, and then you want to count how many of those numbers are multiples of a given number d. And whether, if you can do that accurately enough, you could try to plug it into a formula of this type and then see what you get. Okay? Now, the only trouble with this is that even for a nice sequence of integers, nice sequence like the integers up to x, what I can say is just that the number of prime integers up to x that are multiples of a number d, I can say that this is roughly equal to, this is exactly equal to the floor of x over d, which is just x over d with an error that's at most 1. Okay? So here let me say that if I say theta times 1, I mean that theta is some number which is less than 1 in size. Okay? So let's just say theta is less than equal to 1. Think of it as big O of 1, but it's big O of 1, but the constant is actually 1. Okay, now I could plug that in here, and then the main term looks nice enough. The main term would be x times the sum over d divides this product over d, which looks quite nice. It's x times the product over primes up to root x, 1 minus 1 over p, right? And maybe you can tell me what this is asymptotically. Or it'll be covered in the exercises after 3:30. So Metten's theorem kind of tells you what asymptotics of the product of the primes up to some point of 1 minus 1 over p is. So this product is p up to z, 1 minus 1 over p. That's this constant e to the minus gamma over log z, asymptotically. Yeah?
That can't be right. As z increases, the product should increase.
The product is yeah. Its terms less than 1. So it certainly decreases, right? Okay. Okay, so but I can still plug it in here, and then this would be asymptotic to 2 times. So okay, x times e to the minus gamma divided by log of root x, right? Log of root x. But then that's the same as putting a log of x here, and then the 2 goes to the numerator, right? And you were right anyway. This still can't be right, because it says that 2e to the minus gamma, if the prime number theorem is correct, should be equal to 1. right? So for 2 e to the gamma minus gamma is not equal to 1. So what went wrong? Well, you can see that what went wrong is that I only evaluated the main term, and I didn't do anything with these remainder terms at all, even though these remainder terms are very small, right? They're not very small if d happens to be bigger than x. If d happens to be bigger than x, the main term will be less than 1. And, there are no numbers less than x. There are multiples of a number d that's bigger than x. And you can see that this remainder term is absurdly large. The remainder term would be counting an error of 1. You should forget the sign, because you don't know what this error is going to be. Maybe it's close to 1 when the Möbius function is plus 1, and it's maybe close to 0 when the Möbius function is minus 1. But if you now forget the sign of the Möbius function, you'd have the total number of divisors of the product up to root x of p, and that's a huge number. It's like 2 to the number of prime factors primes up to root x. Okay? So the main term is on the scale of x, or x over log x, but the error term is exponential in x. Okay? So there's no hope of an asymptotic formula by just doing inclusion-exclusion so naively as this. Right? And that's good because this equality is not true anyway. So this constant doesn't work out. Okay. Another way to see that this constant can't possibly work out is that you could say, I said every number that's composite up to root x, up to x, must have a prime factor less than root x. But I could equally have said that every number that's composite up to x must have a prime factor below x to the 2/3, let's say, right? Or x to the 3/4, or whatever. If I carried out the argument that way, then instead of having this truncation at root x, I would have had the truncation at x to the 2/3 or x to the 3/4 or whatever. And obviously, this main term can't really match up for all those values of x, because this will change. But so will the remainder term. Okay? So this is the place at which a point at which sieve methods start. There are various combinatorial ideas to make this better. The main person who initiated this was Viggo Brunn, almost 100 years back now. And his insight was that you try to get upper and lower bounds on this quantity, the number of primes up to x, by not summing over all of the terms that appear in inclusion-exclusion, but you only sum over some number of them. For example, the inclusion-exclusion principle has the feature that you can get, let's see, how does this go? If I stop after an even number of steps in the inclusion-exclusion formula, I get a lower bound. If I stop after an odd number of steps, I get an upper bound. And then you can play around with that. And then, and then your main terms, you'll have to work hard to show that they are actually approximating this main term. Okay? But then the error term might be more in control because you will not have to sum over all the numbers composed of primes less than root x. You might have to only sum them up to numbers having, dividing this, but having only, say, 99 prime factors or 100 prime factors or so on. Yeah? So there's some advantage there. Okay. So you can play around with truncating inclusion-exclusion appropriately. And in this way, Brunn was able to show, for example, that if you count the number of twin primes up to x, Dimitris mentioned that we believe that there should be an asymptotic formula for this, that it's like some constant times x divided by log x squared, and then Brunn gave an upper bound that was bounded by some constant times x over log x squared. Now, So today I want to talk about a different sieve method, which is due to Selberg. I think in some version he did, but then I think he actually had a version that does not miss any log logs. Yeah. I haven't actually looked at those papers, so I don't quite know. But I believe that he did not actually miss any log logs eventually. Right. So, okay, so let me tell you, a couple of things that come out of this Selberg sieve, and then what I want to say is that it doesn't just allow you to understand something like how many primes there are up to x, which in any case we understand by analytic methods, but in fact it tells you some things which you really cannot get your hands on in any other way. Okay, so for example, instead of just asking about the number of primes up to x, we are also interested in how many primes there are in an interval from x to x plus y. Okay, and so here we should always think of y as being something substantially smaller than x. If y is like x or bigger than x, then it's really just the prime number theorem. The prime number theorem would allow you to say how many primes there are between x and 2x. You just use it twice, once with x and once with 2x, and subtract. Right? And so, but if you think of y as being substantially smaller, Demetrius mentioned that the prime number theorem would have an error term which is roughly like square root of x. Okay? So if you plug in the prime number theorem at x and x plus y and you subtract, you'll have a remainder term which is like square root of x. You can't subtract error terms. You can subtract the main terms, but not the error terms. So if you do that, you see that you cannot, even if you knew the Riemann hypothesis, get an asymptotic formula for this if y is like square root of x or x to the 0.49, say. Okay? If y is x to the 0.51, that would be okay, at least on RH, but not for smaller values of x. So what does Selberg sieve give? It allows you to give estimates like this. So this is a theorem that comes out of this, that the number of primes in an interval from x to x plus y is no more than twice the number of primes up to y. Okay? And this is true for all values of x and all values of y. Let's say y is at least 2 or something like that. So that So it's a pretty remarkable theorem. It tells you that if you take any interval of length 1,000, the number of primes in that interval cannot be more than twice the number of primes up to 1,000. Okay? Yeah. Is that sharp or? We don't know, right? So for a while, initially there was some kind of a conjecture due to Hardy and Littlewood. They conjectured that maybe, so actually I'll say why I put the quotes here. You might guess that the number of primes between x and x plus y should be no more than the number of primes up to y. Right? You move your intervals far enough, the primes keep thinning out. So maybe if you're far out, then the number of primes in that interval should be no more than what you had in your initial segment. Okay? So I put quotes because in their paper I actually don't find anywhere that they actually stated this as a conjecture. There was something vaguely related to this, closely related to this that they say, but not exactly this. Okay? And they also made another conjecture, which is the conjecture that Demetrius talked about today morning very briefly, about counting the number of twin primes or generalizing it to count the number of k tuples of primes, n plus h1 to n plus hk all being prime. Okay, this is the k tuple conjecture. So I think in this course we'll come back to this conjecture over and over again. So if you don't recall this completely from Dimitris's talk, you will have many more occasions on which we will talk about this, or somebody will talk about this conjecture. Probably not me. Anyway, and this is widely believed to be true, this k-tuple conjecture. So some generalization of the twin prime conjecture. And it turns out that these two conjectures are actually inconsistent. Okay, so in other words, you can kind of see what's going on here. The k-tuple conjecture kind of tells you, if I give you a k-tuple and I want all of them to be prime when I shift it around, it tells you that under certain natural assumptions, you can always make them to be prime. Okay? But if you can now find an admissible set of numbers up to y, okay, and the cardinality of that set is bigger than the number of primes up to y, then the k-tuple conjecture would say that way out, all of them can be made to be primes, and then you would have a contradiction to this first conjecture. Right? So we all believe that this conjecture is true. Okay, and so therefore we all believe that that conjecture is false. All right? But on the other hand, whether this constant here should be 2 or 1, nobody really knows. Okay? You might believe that it's kind of 1. You know, maybe it's off by just a little bit from being 1. But at the moment, no one has any clue. But one thing that's funny is that even though most people believe this and most people don't believe this, very recently I found that there's a lot of crank literature which is obsessed with this conjecture and proving this conjecture. So I don't quite know why. I mean, at least it's reasonable to try to prove Fermat's last theorem or the Riemann hypothesis or some other things. But it's not reasonable to try to prove this. So, okay. So that's a theorem which I hope you can see is a very remarkable theorem. It holds uniformly in x and y. Okay. Another version of this, again that follows from Selberg's sieve, is to count the number of primes in an arithmetic progression. You can again say that this is bounded by, so I'm going to just write down the asymptotic formula, but you can probably write it a little nicer. Again, this is bounded by 2 times x divided by phi q. So if I put a log x here, then that would be exactly, so if I pretend that I had an x here, then x over phi q log x is the main term that you're supposed to expect for primes in arithmetic progressions, right? So maybe uniformly up to something like root x or something like that. And then this extra factor 2 is like that factor 2 that we had in this estimate for primes in a short interval. And notice that guy would be roughly like y divided by log y, not y divided by log x. Yeah? So similarly here, I should be dividing by something that corresponds to y instead of x. So the analog here is to write x over q. Okay? But apart from this change, these two inequalities are kind of very much of the same flavor. Okay? Now, I've written it as an inequality. I think it's actually true as an inequality. I probably won't prove it this way. But you can imagine if I wanted a little way to escape, maybe I should put a 2 plus epsilon here. But I think it's actually true as an inequality. Okay? Here? So there should be, I believe it's true without that, it should be a result of Montgomery and Vaughan, just as this one with no other constants is true as an inequality. Okay? But anyway, it doesn't matter. It's very clean if I write it as x over q. It's a little less clean if I write it as 2 plus epsilon, but theoretically it makes no difference. Okay? And this would be true for, again, we should make some assumption, maybe that q, let's say, is at least 2, and at most, let's say, x over 2 or something like that. Okay. Now, so these two results are known as some versions of these are known as the Brun-Tishmarsh theorem. And if I want to write them as exact inequalities, the inequality versions are due to Montgomery and Vaughan. Although I think you can also get them, maybe they're due to Brun-Tishmarsh is less than Montgomery-Vaughan. Goes in the right direction. So it's also, there's some very clever versions of this in Selberg's notes on sieves, lectures on sieves. Okay. And then you can imagine you can kind of do some mix and match and also try to do something like count the number of integers in an interval from x to x plus y, and then, or count the number of primes in x to x plus y with p being congruent to a mod q. And then try to bound this. Okay? You can do this too. So this is kind of a prototype of a whole number of other results that you can do by the same method. So to explain this, let me just focus on the first of these theorems, that counting the number of primes in a short interval, and I'll try to show you how the method works in this situation. Okay. Okay, so now let's say we want to count the number of primes p between x and x plus y. Right? Now, well, certainly what I can do is I can assume that there's a parameter r is some parameter. And then I can say bound this by the number of integers n up to in this interval from x to x plus y. All the prime factors of n are bigger than r. Okay? If you think of r as being like x, then of course I will exactly be getting the number of primes between x and x plus y. Or even if r is like root x, I'm essentially getting the primes between x and x plus y. Okay? But for any value of r, this is kind of an upper bound. This okay? Right? So then I can try to understand this object. And what you might guess would be, well, maybe I should let you guess what you think would happen. Not looking for anything fancy, just that, okay, that the larger I make r, the harder problem I have, right? But the better my bound is going to be. Okay? So the larger I make r, probably the harder it gets to understand this, but it approximates the situation closely. And then conversely, the smaller I make r, maybe I'm not really modeling this nicely, but I might expect to understand this extremely precisely. Okay? So those are the two things in sieve theory. So in the Selberg, to get the Brun-Titchmarsh theorem, we will just pretend that R is like X or root X. And then this will lead us easily to something called to this Brun-Titchmarsh theorem. Once I put in the Selberg sieve, which I haven't explained yet. And then the other part of sieve theory is that if R is a small power of X, let's say R is like X to the 1 over a million, right? Then in this case, so I have to be careful here. Okay. So R has to be small not just on the scale of X, it has to be actually small on the scale of Y. So let's say it's Y to the 1 million when it's really small, right? The quantity of importance is not where my interval starts, but it's the length of the interval that's going to govern everything. So if it's a small power of the length of this interval, then I can understand this extremely closely. Good formula for this. What does extremely close mean? Well, I actually don't have an actual asymptotic formula, but it would be accurate to within 10 to the minus 10 to the 6 times 10 to the 6. Okay? Which is pretty good by any standards. Right? And then this aspect of it is called in many ways, is in many variations, something called the fundamental lemma of sieve theory. Okay. So I'm going to explain Selberg's sieve in a slightly flexible way, introducing this parameter R, which at the moment makes no difference, but all that I'm going to say you could kind of use to prove some easy version of this fundamental lemma of sieve theory as well. And again, maybe you can ask Zeb to tell you more about this in one of the discussion sessions. Okay, so how does this Selberg sieve work? It's based on a very simple idea. The idea is that if X is a real number, maybe let's say T is a real number, then T squared is positive, right? And we're going to use this in a very clever way. So there are going to be some real numbers lambda of D, with lambda of 1 being equal to 1. Okay? And let me assume that lambda of D is 0 if, say, D is bigger than Z. Z is some parameter that I'll choose for you later. And lambda of D is also 0 if D has some prime factor bigger than R. Okay? So the lambda D's are non-zero only on the numbers less than Z and on the numbers that are composed only of prime factors up to R. All right? And then I'm going to form for some number n, I'm going to look at the sum over the divisors of n of lambda of D squared. And this satisfies a couple of inequalities. Well, firstly, it's greater than or equal to 0 always, right? Because every real square is positive. And it's also at least 1 if, well, if what? If n doesn't have any prime factors up to R, right? If n doesn't have any prime factors up to R, then the only divisors of n for which lambda D is not equal to 0 is D equals 1. And there I'm assuming that lambda 1 is 1. So it's bigger than 1 if p divides n implies p is bigger than r. Is this good? Okay, but now this means that the number of integers up in my interval x to x plus y with counting only the numbers all of whose prime factors are bigger than r, by this inequality, this is at most the sum over n between x and x plus y squared. Okay. And now let me expand this object out. So if I expand it out, I have two parameters, d1 and d2, lambda d1, lambda d2, right? And then I have to count the number of integers between x and x plus y that are multiples of both d1 and d2. Okay? If a number is a multiple of both d1 and d2, then it must be a multiple of the least common multiple of d1 and d2, the LCM d1 and d2. So let me put throughout, this is the LCM of d1 and d2, which is nothing but the product of d1, d2 divided by the GCD of d1 and d2. Okay, so now what I have to count here is the number of integers in my interval from x to x plus y that are multiples of the LCM of d1 and d2. Well, that's no more than the length of the interval divided by the LCM d1, d2 plus at most 1 for some theta less than 1 in size. It's okay? So this theta could depend upon d1 and d2. So okay. Now, so let's simplify this upper bound a bit. So I have a main term which is y times over the LCM of d1, d2. And then I have an error term, or writing everything explicitly, that number theta is less than 1 in size, and therefore what I have here is the sum over d, the size of lambda d, and the quantity squared. Right? When I square it, I get d1 and d2. Okay? This is an actual inequality. Yeah? Now, let me not worry about this. Let me hope that this is an error term that's actually small. Okay? In which case, I can forget about this for the time being. And if I just think of what the main term is, then the structure of the main term is that this is a quadratic form in the lambda d's, right? Subject to some conditions. Lambda d is 0 unless d is less than z and composed only of prime factors less than r. And And then I have this main condition here that there's a linear constraint in the lambdas that must be satisfied, that lambda 1 should be 1. Okay? So now we have a very simple optimization problem. Minimize this quadratic form. While subject to the linear constraint. Lambda 1 is 1. Okay. Now, this problem was fully solved by Selberg. What we've realized in the last 10 years, starting with GPY, is that for the applications to gaps between primes, or their first result and also the recent results on bounded gaps between primes, that this is somehow not the right problem in this, for this particular framework for gaps between primes. And the problem really happens to be minimize some quadratic form subject to some other quadratic form being fixed, or the ratio of two quadratic forms. So that will become clearer later on this week and over the next week. Okay, but for the pure application to the sieve, this is the optimization problem that we've come up with. So how do we do this? One idea which was carried out by Selberg is that we just diagonalize the quadratic form. Okay, so how do we do that? So my quadratic form is d1, d2, lambda d1, d2, divided by the LCM, which as we noted is d1, d2, times the GCD of d1 and d2. Right? Without the GCD, it's already kind of diagonal. Right? It's just a square. So how does this GCD affect us? Well, one way to think of that is to use this, we have this elementary formula that if you sum the Euler phi function over the divisors of a number, you get back the number itself, right? Take all the fractions 1 over n, 2 over n, up to n over n, put them in reduced form, and then that's your identity. So I can now rewrite this as a sum over numbers, let's say L, that divide both d1 and d2 of phi of L. Right? Now then if I exchange the two sums, then what I have is a sum over L, phi of L, may be divided by L squared, that divides d1 and d2. Let's put L squared here. And then here I get a sum over d lambda of LD divided by d squared. Right? So, okay. So what do I have here? Think of this as a sum over multiples of L. D1, L divides D1, so D1 must be a multiple of L. So that's all the multiples of L. And squaring gives me the two variables, D1 and D2. Okay. And you can see that I've now diagonalized my quadratic form. Right? So this is a diagonal quadratic form in these new variables. Okay, what are the new variables? Let's write this as C of D, which is equal to the sum over, no, C of L, let's say, is the sum over D lambda of LD divided by D. Yeah.
That's D in the denominator underneath lambda of LD?
Yeah. Right. Yeah. Because there was a D in the denominator here, right? And I wrote this D1 as L times D, if you like. And then this one is L times D again. So there's an L squared that factors out. And then it's this.
Yeah, it looked like it was in the subscript.
Yep.
It's like,
So far, so good? Okay. Now, again, these C's are not arbitrary. The lambda satisfies some constraints. So therefore, the C's also satisfy some constraints. Right? So for example, CL would be equal to 0 unless L is less than Z and L is composed only of primes below R. Right? If L is bigger than Z, then all the multiples of L will be bigger than Z. They're all 0. If L is divisible by some prime bigger than R, then all the multiples LD will also be divisible by that prime bigger than R. They're all 0. Okay. Now, what happens to the constraint that lambda 1 equals 1? How does that translate as a condition on the C's? Okay. Or another way to put it is that you might be worried that I've made some linear change of variables here. I should make sure that this linear change of variables is invertible, that every choice of the X's corresponds to a possible choice of the lambdas. Right? So we can do both of those in the same way using Möbius inversion. So let's invert the change of variables. By basically Möbius inversion. Okay, so I have to remember this every time, so let me try to do it like this. I want to understand lambda of R. I want to rewrite it in terms of the X's. Let me write lambda of R as lambda R times, let's say, A divided by A. And let's say that A must be equal to 1. Right? If A is exactly equal to 1, then this is okay. So this is 1 if A is 1, 0 if A is not 1. But I know how to write that with Möbius inversion. So let's say put a sum here over all A. So this is just a sum over D divides A, the Möbius function of D. This is equal to 1 if A is 1 and 0 otherwise. So now let me just regroup the terms. It's a sum over D, mu D, and then a sum over A, lambda AR over A, with D dividing A. Right? And see, this looks a lot like the definition of Xi. So write A as D times B, let's say, and then take a D out. Over B. Right? And this is just my definition of Xi of dr. Yeah? So that's a sum over D, mu D over D, Xi dr. Okay. This means that I know, so the change of variable going from lambda to Xi, I can invert it. And it also tells me what my linear constraint means in terms of the X's. So the constraint that lambda 1 is 1 is the same as saying, just use this with r equals 1, the sum of mu d over d times cd is equal to 1. Okay. So now we're almost done with our proof because we have that linear constraint, and then I have to optimize this quadratic form. So under this linear constraint, we want to minimize the sum over L, phi of L over L squared, Xi sub L squared. Okay. So again, keep in mind that Xi of L is 0 unless L is less than Z and P divides L implies P is less than R. Okay? Now, okay, so how do I optimize this? How do I minimize this? Well, I could do a number of things. I could either use Cauchy-Schwarz connecting this to that, right? Or you could kind of guess that the only way in which, if I have this linear constraint and I want to optimize this quadratic form, it's kind of roughly if the two objects kind of look like the same. Okay? So the choice might be, so either think of Cauchy-Schwarz and the equality in Cauchy-Schwarz, or think of calculus as in Lagrange multipliers, or just think about it for 2 minutes. And you can see that the choice should be that Cl is proportional to okay. This constraint kind of is only supported on square-free numbers, right? Because it has a Möbius function here. Yeah? And I have everything here being positive. I should certainly make these CLs to be 0 unless L is square-free as well. Something we didn't know before, but it really has to be that way. If I really make these two things, if I just kind of match up, then what I should get is that it should be approximately mu L times L over phi L. Phi L times some constant of proportionality. Okay? So let's say it's equal to this. Let's say it's equal to 1 over L, some capital number L times mu L times L over phi L. Okay. Again, only on those numbers that are below Z and have all their prime factors less than R. Otherwise, I take it to be 0. Okay. With this notation, the linear constraint is just 1 over L times the sum over L less than Z. P divides L implies P is at most R. Plug this in there, you get mu of L squared divided by phi of L. The L in the numerator here cancels with that D in the denominator there. D is the same as L. Okay? So that's the linear constraint. So this equals 1 is the linear constraint, or in other words, L is just equal to this quantity here. Okay? And what's the quadratic form? Well, it's the same thing. It's 1 over capital L squared times the sum over L up to Z. P divides L implies P is at most R. Well, let's square this. You get L squared times mu L squared divided by phi L squared. L squares cancel. One of the phi L's cancels. So you get, again, mu of L squared divided by phi of L. Right? Which, again, 1 over L times this was equal to 1, so this is just equal to 1 over L. Okay? So the main term in the optimum choice of these X's gives for our main term a very elegant answer. It's y divided by L, right? And L is just the sum over L up to Z. P divides L implies P at most R. Mu L squared over phi L. Yeah. Correct. Okay. So should I go for 5 minutes more? Because we started a little late. Or should I stop?
So in the application to interval problem, the role of x is hidden away in the choice of R.
The role of x in this case is kind of okay, so firstly, let's talk about the role of x, right? To do that, we should first maybe appreciate what the role of z is, okay? At this stage, let me also say that it makes no difference if r is bigger than z, what r is, right? Once r is bigger than z, this condition just goes away, yeah? So let's pretend for the moment that I will either make r to be z or r will be something smaller than z, right? It makes no sense to take r bigger than z. But what we'll see is that I haven't talked about the remainder term there, which I should talk about now, which will give me a constraint on z. It will tell me that z cannot be chosen much bigger than square root of y. Okay? So in that sense, you could say the role of x is kind of completely goes away, right? But you can also see that in the inequality that I wrote down, pi of x plus y minus pi of y is less than twice pi of y. The right-hand side had no x in it as well. Okay? Another way to say all of this is that the number of primes in an interval from x to x plus y, if you just subtract the main terms in the prime number theorem, you might expect to be less than y over log x. But that, of course, makes no sense if y is like and there happens to be a prime between x and x plus 2, right? Okay, so x, you don't expect to find answers depending on x in this setup. Okay, so that's the bound that we have. There are a couple of things that we have to understand. One is what I just mentioned. We need to understand how big z is. Again, the bigger the z is, the better, right? But there will be a limitation on z coming from the remainder term that we haven't discussed yet. And then after that, we might still need to understand what the asymptotics of this sum are. Okay? Maybe let me come back to that tomorrow and then just try to finish that up. Let me just now say what happens to the remainder term. What about the error term? Well, I should probably try to understand what the size of C is and then plug it back in to try to understand what the size of the lambda r's are, right? And then I plug that back in here to understand how big that sum is. Okay? So we can do this kind of nicely. So lambda of d from our formula there, lambda of r, let's say, that's at most the sum over d mu d c dr over d, right? Just writing down my identity for what c of d is. Now let me plug in what c of dr is. So that's 1 over L, and then a sum over d, mu of d, mu of dr times dr over phi of dr. So r over phi of dr. Is okay? So let me just assume we might as well assume that there's no interaction between d and dr that I can exploit. Well, actually, I can't, right? Because so long as dr is a square-free number, this times that, its sign will just be the Möbius function of r, and it doesn't change sign as d varies. So let's just say this bound is just bounded by 1 over L, the sum over d. Well, so dr must be square-free. So let's put mu of dr squared here, and then an r over phi of dr. And then the condition here will be that dr must be at most z, and then that dr is composed only of prime factors up to capital R. Right? Okay. And then what is my bound? My bound was the sum over r, lambda of r, well, and then I'm going to square this as well, right? So let's just plug this in here. So this will be bounded by 1 over L, the sum over d, and the sum over r, with dr at most z, composed of primes at most r, mu of dr squared over phi of dr times r. So in other words, if I group terms according to dr equals some number n, I get mu of n squared over phi of n, and then a sum over the divisors of n of r. Okay, so this actually is equal to some sum like n up to z, composed only of prime factors up to r, mu of n squared, sigma of n divided by phi of n. Sigma of n is the sum of the divisors of n. Right? Think of n as d times r, and I'm summing this r. Okay? So maybe I'll stop here after saying 2 words. I've kind of written it down so that you have actual inequalities everywhere, right? So you have an actual upper bound for the number of primes in this interval, no big O terms, nothing, so just an actual honest-to-goodness inequality. Then you have to understand what these functions behave like. Sigma of n usually behaves just like the number n. Like you would have seen in your discussion session before lunch, that phi of n also kind of roughly behaves like n. So this is just like 1. So this quantity here is of size z, basically. Okay? So the error term is of size z squared. We are shooting for a main term which is of size y divided by log y or something like that. So this kind of tells you that there's a restriction that z can go up to roughly square root of y. Okay? So this constrains z roughly to be of size square root of y. And actually, the way we worked it, you can actually take z to be a tiny bit larger than that. And that's useful if you want to prove this estimate with the actual constant 2 with no remainder term involved. You can kind of eke that out of the version that I've described. And then the last thing that needs to be understood is what this parameter L, how it behaves. And we'll show that it actually behaves roughly like 1 over log y, at least if R is suitably big. So I'll finish that off tomorrow morning, and then also explain that even though this is an upper bound, if R is suitably small, you can leverage this to actually get an asymptotic formula for the number of integers in an interval that all of whose prime factors are bigger than R. Okay, so we'll finish that tomorrow. Thanks very much. Yep.
So in the middle one, you wrote psi L is 1 over L mu L L EL.
Yep.
So does that always hold, or do you choose your lambda so that it satisfies that?
So I can do both ways, right? Okay. Because this linear change of variables is invertible, I can choose my x's, and then it tells you what lambdas are. Okay? So I'm going to choose xi to be this way, and then lambda is chosen in a certain way, right? Basically like so. So maybe let's discuss that tomorrow morning, or you can think about it and then I can ask someone to say what they found for the lambdas tomorrow. You can see, if you choose the x's this way, you should try to think for yourself about what does lambda look like, right? So a guess might be that lambda should have something to do with the Möbius function, right? You're trying to find primes. When we did our initial inclusion-exclusion, we had the Möbius function show up. So you might want to ask this choice for x's, what does it mean for lambda?
With that L, I guess.
Yeah, with that L, exactly, right? Yeah, and you should see something nice, which we can pick up on tomorrow. Other questions?